Okay, next one is page 1. So state 1 is meant by internal energy. Again, it's the same definition from before. This one is worded differently than before. Sum of potential and kinetic energy of molecules in a system which are in random motion and randomly distributed. This one is actually an old definition from the marking scheme. You can use this, but you can also use the definition that I've put in the notes for you. The one that I put in the notes for you, where you say the internal energy is the sum of a random distribution of kinetic and potential energies of molecules in the system. This is actually the best one to use, okay? So just use this one, right? So don't bother with the ones that I've just written here. Just use the one that you have in the notes. Okay, then you move on to B. The variation with volume V or the pressure P of an ideal gas as it undergoes cycle ABCA of changes is as shown in figure 2.1. The temperature of the gas at A is 290 Kelvin and the temperature of B is 870 Kelvin. They mentioned to you subsequently to find out the amount in mole of the gas and the temperature of the gas at C. Okay, so this one again may not be directly related to your current chapter. This one requires you to know a bit about ideal gas. So to find out the amount of mole of gas, you again use PV equals to nRT applied for point A. Find out the pressure, the volume, equate it to nRT. You will get your number of moles at 0.199 moles. This one is if you equate it, if you apply PV equals to nRT for point A. You can likewise apply it for point B and get the same answer. It doesn't matter which one you use. You have the complete information for point A as well as for point B. Okay? Right. Then after that, if you move on to part 2, you are not trying to find out the temperature of the gas at C. You again use PV equals to nRT. You know the pressure, you know the volume, you know the molar gas constant, and your number of moles is actually what you found from the question above. Because it's a closed system where they didn't mention anything about adding gas or removing gas, is going to be same number of moles. Okay, so your number of moles that you use here is the same as the one you find above, eventually giving you temperature as 562 Kelvin. Okay, so there's no issues here. Now for part C, they want you to explain why the change from C to A involves external work and a change in internal energy. Okay, so if you recall the graph that you had just now, it looks something like this. Okay, where it was going from A to B to C, A to B to C, and this is a pressure volume graph. So you go from A to B, B to C, C to A. So they want you to explain why is there external work and why is there change in internal energy for your current case, just from C to A. Now, if you look at your graph, you will notice that from C to A, there's a decrease in volume. So there's a decrease in volume. Work is done on gas. Okay. This one is one thing to note. And then when you look at the temperature changes, this one was 562 Kelvin, then it went up to 800 Kelvin, is it? Sorry, it was 562 Kelvin, then it went down to 290 Kelvin. Okay. So this one, if you look at the relation between internal energy and temperature, IE was equals to KE for ideal gas. KE is proportional to temperature. Combining those two together, IE is proportional to T. Okay, so in your current case here, you could have said that from C to A, temperature decrease, so your internal energy decrease. And then for the first part above, your volume decrease, but it's done on gas. So you have positive delta W. That's what you would have normally deduced from here. Okay. But when your question is asking you this to explain why there's external work and there's change in internal energy, they are looking for something a bit more general. They are not really asking you to explain whether the internal energy is positive or negative, whether your work done is positive or negative. Because like how I explained it here to you, this one I told you that your work done is positive. And then the second part here where I say the internal energy is proportional to temperature, because you're having a decrease in temperature, your internal energy is dropping. This one will tell you you have negative internal energy, right? This one will tell you that you have negative internal energy. Okay, but you don't need to explain to the level where you need to explain why is positive delta W and negative delta U. What they're really looking for here is whether there's any change or not. So your answer was really more of a general kind, where they say that because they see that there's temperature change, internal energy change. And then because they see that your volume is changing at constant pressure, therefore work is done. Now, when they say external work here, it just means any type of work. It can be work done on or by system. It doesn't matter whether it's on or by. If it's work done on system, if it's work done by system, it's still considered external work. Okay, so this one here, your answer is more of a general kind to explain whether there's any change in the first place. But you're not required to explain the nature of the change, whether it's positive or negative, whether it's increase or decrease. You just need to explain why is there a change. For internal energy, it changed because temperature change. For external work, it's there because there's volume change. That's all there is to it. Okay. So this one should be okay. Okay, then next question that you can have a look at is probably page 7. Okay, so next question is page 7. Okay, so if you just have a look at page 7, state an expression in terms of work done in heating that is used to calculate the increase in internal energy of a system. This is actually referring to your thermodynamic first law. You just need to say that the increase in internal energy is equal to heat energy supplied to system plus work done on system. That's all. You don't need to bother about the variables that I wrote here, as well as the equation that I wrote there. You don't need to write that in. You can just write them all fully in words. Increase in internal energy is equal to your heat supply to system plus work done on system. Because it's trying to describe this equation here when all of them are positive. Okay. Now, if you move on to part B, state and explain in terms of your expressions in A, the change, if any, in the internal energy. Now, when they see state and explain in terms of state and explain in terms of expression in A, this one is asking you to explain using thermodynamic first law. The question has already told you to explain using thermo first law. Expression in A was thermodynamic first law, isn't it? Because sometimes when you try to explain internal energy change, there are actually two different ways to go about that. Is either from definition of internal energy, where you say internal energy is equals to KE plus PE of molecules, such that change in internal energy is equals to change in kinetic energy plus change in potential energy. This is one way to explain changes in internal energy from definition of IE itself, or sometimes they call it from using molecular energy. Right? Explain the change in IE using molecular energy. Another one is from thermal first law, where you say increase in internal energy is equal to your heat supplied to system plus work done on system. So there are two different ways to do that. But your question here specifically asks you to use thermodynamic first law. Okay. So you tend to explain it in terms of heat supply as well as work done. Now, for the first situation that you have here, what is the internal energy change of water in an ice cube when ice melts at atmospheric pressure to form liquid without any change in temperature? Okay, so let's just consider this first. If say for example you had ice, this one is ice, it melts to become water. What I'm interested in is the work done to this system from ice to water. From some of the examples that we've done just now, you know that you have work done when you have volume change. If there's no volume change, there's no work done. This one is, I think, mentioned in the notes right over here. Generally speaking, if there's no volume change, there's no work done. If you have volume change, you will have work done because it's already implied from this equation here. W is equals to pressure times volume change. So what you're interested now is to find out when ice changes to water, is the volume increasing or decreasing? So let's consider this. If I say that your ice was 1 kg, when it melts to become water, the mass will still remain the same at 1 kg. Okay? But how about the density? If I compare the density of ice and water, the densities are actually different. Because what you do know is that ice floats on water. This one would mean that the density of ice is actually less than the density of water, isn't it? Okay, so how does this relate in you trying to find out the volume, whether it increases or decreases? You need to make use of equation for density. Density is mass over volume. If we know that mass is constant, that means density is inversely proportional to volume. Okay, so now if I'm talking from ice to water, the density is actually increasing, isn't it? Because here I already mentioned to you that density of ice is going to be less than water because ice tends to float on top of water. If you're going from ice to water, that means your density is increasing. So density is increasing. Therefore, your volume decreasing because there's an inverse relation here. Okay, so I know that from ice to water, my density increases, so my volume must decrease. So if I know that my volume decrease, work is done on system. Therefore, you have positive delta W. Okay. This one explains the work part. You now want to focus on the heat supply part. Okay. So for the heat supply part, you can probably think of it this way. Heat is supplied to break the lattice bonds from when ice melts to become water. When ice melts to water, lattice bonds are broken. Thus, heat is supplied to system. So therefore, you have positive delta Q. In order for you to break the lattice bonds in the first place, you need to supply heat. You cannot say you release heat and then bonds are suddenly broken, isn't it? So heat must be supplied here in this case. So from these two explanations, you can actually see that work done is positive, heat supply is also positive. Okay, so for your thermodynamic first law, if your delta W is positive and your delta Q is positive, obviously your delta U will be positive. Also, your internal energy is increasing. Okay, so how will you actually write your answer? Okay, because you see the explanation here on the right seems to be a bit long. What I can suggest you to do is probably you write this first answer here. You say that when ice melts to water, the volume decrease, so what is done on the system is positive delta W. Okay, and then the second thing you could write is probably this. Thermal energy is absorbed or supplied to system to break the lattice structure when ice melts to water. So this is positive delta Q. Then the third thing that you could probably say is this, no? Therefore, internal energy increases because both are positive in the first place. Okay. Now, there's also another separate answer that you can write in place of number one. Sometimes they could also tell you this. Your marking scheme actually accepts both. When I explain to you the volume change for ice to water, it is correct to say that the volume decreases, but it's very little. There's a very little decrease in volume. Okay, so sometimes the marking scheme will also accept you saying that the volume change is too little, so work done on system is negligible. This one would mean delta W is 0. Okay, so other than writing point number one here where I say volume decreases, you can also write this other point to replace that if you wanted to. This one you could probably write this in place of point number one if you wanted to. You can here say that there is negligible change in volume or very small change in volume, so work done is negligible. So delta W is 0. Either one will be acceptable. Marking scheme accepts both. If you say that volume change is negligible, they accept. If you say that volume is decreasing, they also accept. Okay. It doesn't affect your final answer at the end. Because if you try to look at the thermodynamic first law, you're saying that there's negligible change in volume, so work done is negligible. Delta W is 0. That would mean this one is 0, but you still have heat energy supplied to break the lattice bonds. So this is positive. So if this one is 0, this one positive, obviously your internal energy would still be positive. It will still be an increase. Okay, so it doesn't change your answers at the end of the day. Okay, so just use whichever you like. For me personally, I will always use volume decrease. Okay, when it comes to explaining the changes in internal energy. Okay, now then after that, if you move on to number 2, what happens to the internal energy of gas in a tire when the tire bursts so that the gas suddenly increases in volume? Assume that the gas is ideal here. So for this case, you again want to look at it in terms of the work done, in terms of the heat supply. So how are you going to look at it? The easiest one will be to probably look at it in terms of the work done first. Say right now, you have a tire like this. That tire contains a volume of gas. They say it's ideal gas. So at some point, that tire suddenly bursts. Maybe there's a puncture somewhere here. So because there's a hole right now inside your tire, the gas that has been contained inside the tire will now flow out. It will now expand. So from here to here, what you could say is that your volume has increased, work is done by system. So volume increase, work is done by system. Therefore, delta W is negative. Okay, this one I know for sure work done will be negative because I have a volume increase. Okay, then what about the heat supply part? Now, because they give you this keyword, your gas suddenly increases in volume. So because they tell you that it suddenly increases in volume, this one is a very, very short amount of time. So what I could say is something like this. Volume increase suddenly. Because the volume increase suddenly, there is no time for heat energy to enter or leave the system. There's no time for heat energy to enter or leave the system. Therefore, delta Q is 0. Okay. The change in your volume did not occur gradually or over a period of time. It occurred suddenly. So it's a very short amount of time. So because of that, you have to kind of relate it to the fact that there's no time for heat energy to enter or leave your system. Therefore, delta Q is 0. So now if you wanted to then deduce how your internal energy changes, delta W here is negative. Delta Q here is 0. So obviously your delta U must be negative. It will be a decrease. Okay. So how would you word your answer? You can actually just say your volume of gas increases, so work is done by gas. It's negative delta W. And then the next thing you would write is there is no time for thermal energy to enter or leave your gas. So this one is delta Q 0. Therefore, your internal energy would decrease. Okay, so these are your 3 points that you would tend to write here. Okay, now the part where I say volume increases, so what is done by gas, the marking scheme wrote it in a different way. They say the gas expands against the atmosphere, so work is done by gas. It's also meaning the same thing. Because your gas is expanding, your volume is increasing. Okay, so that's for this particular question. Just now you did page 7. There's a similar question again at page 14. So this one you notice is exactly that same question here. Okay, you can actually try it again later in your free time. Okay, next question that you can have a look at is actually page 21. Okay, so let me open it up for you. Right, so have a look at page 21. This is June 18 T42. Okay, now, so for this question here, during melting, a solid becomes liquid with little or no change in volume. use kinetic theory to explain why during melting process thermal energy is supplied. Thermal energy is required, although there's no changes in temperature. Okay. You now have solid becoming liquid. It's kind of like ice becoming water. So they're asking you to use kinetic theory to explain why during the melting process your thermal energy is required, although there's no change in temperature. Now, kinetic theory here refers to you referring to the molecules, because kinetic theory of matter states that matter is made out of molecules or atoms, right? So when they ask you to use kinetic theory to explain why you heat energy in the first place, you have to refer to the molecules. What is actually happening to the molecules or your atoms? Okay. The terms are interchangeable. Sometimes you can call it atoms, sometimes you can call it molecules. It doesn't matter which one you use. So here, what can you actually say? When you're trying to go from solid to liquid, they want you to explain why is heat energy required. So one thing that you could first think of when you go from solid to liquid is this. When you go from solid to liquid, bonds are broken. Therefore, your molecular PE increases. Okay. You cannot say anything about your KE here because temperature is constant. KE change should be 0. If your solid is going to become a liquid, there's actually no change in temperature. So when you try to refer to the molecules now, the first thing you know is that bonds are being broken, so your molecular PE is increasing. But if you're talking about the K of your molecules, you cannot say anything about it because temperature was constant. So now what you do know is that your PE is increasing. Okay. Your PE is increasing. And this can come about due to two things. Your PE is increasing can come about due to work done or heat supply. Okay, if you want to increase the PE, molecular PE of your molecules, you can either come about through work done on the system or heat supplied to the system. So right now, if you refer to this statement here, they say that the solid becomes liquid with little to no change in volume. This one actually kind of tells you that there is little to no work done. Okay, so here, if I give you point number 4, this one they say little or no change in volume. You can actually say that is negligible work done. Your delta W is 0. Okay, so now if you refer to point number 3 here, just now I at least said to you that your P increase must either come from work having been done on the system or heat supplied to the system. But here, because they told you that there's little to no change in volume, it already tells you work done is 0. So your P increase cannot have come from work done. It must therefore have come from heat supply. So that's why your answer here is worded like this. During melting, the bonds between your atoms are broken, thus the potential energy of atoms is increased. And because there's no change in volume, there's no work done. Therefore, your required input energy must be from thermal energy in the first place, must be from heat supply in the first place. Okay, so that's for that part. Now, if you have tried to deduce it from the definition of your thermal first law, as well as your definition of internal energy, you could also come to the same conclusion. That one is actually written in blue above here. The first one is internal energy change is equals to KE change plus PE change. Because temperature is constant, KE change is 0. Therefore, change in internal energy is just change in PE. This one is from your definition of internal energy. Then after that, if you look at your thermal first law, increase in internal energy is equals to work done on system plus heat supplied to system. But because there's no change in volume, work done is 0. Because there's little or no change in volume, work done is 0. So your change in internal energy is actually equals to heat supplied here. If you try to equate these two, equation 1 and 2, you will eventually come to the conclusion that heat supply is actually equals to your PE change. Okay, heat supply is actually equals to your PE change. So therefore, heat energy must be used to increase the PE of your molecules. You can also deduce it from there. This one is a bit more tedious because you have to use two different definitions and relate them together. Okay. But the answer in the marking scheme was actually this one. Okay. The only way to understand this was through what I just explained to you from here and here. Okay, if you had tried to explain it the other way using definition of IE and thermal first law, you will also come to the same conclusion. It's also still perfectly acceptable. Okay, just that it's a bit difficult to explain. Okay, right. So part B will be related to heat capacity and latent heat. This one will be the next thing that I will need to teach you. Okay, this one will be done in the next lesson.